Okay, let's talk about carbon. I mean, it's literally everywhere. It's in the food we eat, the fuel we burn, and in every single living cell of our bodies. You'd think it's the most common thing in the world, right? Well, here's the paradox. For an element that's so incredibly important, it's actually really, really rare. So how can something so scarce be the foundation for pretty much everything?
Get a load of this number, 0.02%. That's it. That's the tiny, tiny fraction of the Earth's crust that's actually made of carbon. In things like coal and petroleum. To put that in perspective, if the Earth's crust was a stack of 10,000 pages, only 2 of them would be carbon. It's a shockingly small amount when you think about what it builds.
And yet, we know of millions of different carbon compounds. That number just blows away the number of compounds from all the other elements combined. So, wait a minute. A tiny fraction of the planet's crust is responsible for millions of different substances. How on earth is that possible?
And that, right there, is the big question we're tackling. What is carbon's secret? How does this one element manage to be the backbone of life itself, and so much of our modern world, when it's working with such a small supply? Well, the answer, it turns out, is all about how it connects with other atoms. It's all in the bonds.
So, to find that secret, we first have to understand the fundamental problem that carbon is facing at the atomic level. It's kind of a big one.
Okay, so here's a fundamental rule in chemistry. Atoms are happiest, or, most stable, when their outermost electron shell is completely full. Think of the noble gases, like helium or neon. They're super unreactive because their shells are already full. They've made it. That's the goal every other atom is trying to achieve. And this is where carbon's whole problem starts. You see, its outer shell can hold 8 electrons, but it only has 4. It is perfectly, awkwardly stuck right in the middle. To be stable, it needs to either gain 4 more or get rid of the 4 it has. And as it turns out, neither of those options is easy.
This really lays out carbon's dilemma perfectly. Okay, option 1, just gain 4 electrons. Well, the problem is its nucleus only has 6 protons. It just doesn't have the magnetic muscle to hold on to 10 electrons. It would be an unstable mess. So, okay, option 2, how about losing 4 electrons? That's also a no-go. It would take a colossal amount of energy to rip those 4 electrons away. So carbon is basically trapped.
So if carbon can't gain electrons, and it can't lose them, what's left? Well, it gets creative. It finds this incredibly elegant solution that turns its biggest problem into its greatest strength.
And here it is, the answer, the covalent bond. Instead of stealing or giving away its electrons, carbon just decides to share. By sharing its electrons with other atoms, it can create a stable, full outer shell for itself and for the atoms it's bonding with. It is a total chemical win-win. Let's look at the simplest possible example to see how this works. A hydrogen atom has 1 electron, but its shell wants 2. So 2 hydrogen atoms get together, each one shares its single electron with the other, and voila! They form a stable hydrogen molecule where both atoms feel like they have a full, happy shell.
Now, let's bring it back to carbon. In a molecule of methane, which is the main component of natural gas, 1 single carbon atom shares its 4 outer electrons with 4 different hydrogen atoms. This one simple move completely solves its dilemma. The carbon atom now gets to share in 8 electrons, a full shell, and each hydrogen gets to share 2. Everybody's stable, everybody's happy.
Now, this whole sharing strategy has a really important consequence. The covalent bonds inside a molecule, like methane, are super strong. But the forces of attraction between different methane molecules, they're pretty weak. And that's why most carbon compounds have low melting points and boiling points, and they're terrible at conducting electricity. There just aren't any free-floating charged particles to carry a current.
But this unique ability to share electrons doesn't just solve carbon's problem. Oh no, it unlocks 2 incredible properties. I like to call them its superpowers, that are the real secret to its unbelievable versatility. So here they are, carbon's 2 superpowers, tetravalency and catenation. First, because it has 4 electrons to share, it can form 4 bonds at the same time. Second, and this one is truly special, it can form strong and stable bonds with other carbon atoms. Let's break these down.
First up, tetravalency. Tetra just means 4.
This means a single carbon atom acts like a little construction hub with 4 different connection points. It can reach out in 4 directions at once, which allows it to build these amazing, complex, 3-dimensional structures.
And now for the second and arguably even more amazing superpower, catenation. This is carbon's almost unique talent for linking up with itself over and over, forming incredibly strong and stable bonds. Sure, some other elements like silicon can kinda do it, but their chains are weak and fall apart easily. Carbon-carbon bonds, on the other hand, are built to last.
This table is just a perfect example of catenation in action. You can see carbon atoms just linking up, one after another, to form these long, stable chains. We go from 1 carbon in methane to 2 in ethane, 3 in propane, and so on. These chains can be hundreds, even thousands of atoms long.
So let's bring this all together. These 2 superpowers, tetravalency and catenation, working hand in hand through covalent bonding, that is what allows this one rare element to create an entire universe of different compounds. And there is no better example of this than diamond and graphite. Both of them are 100% pure carbon. That's it. But just look at how they're built differently. On the left, in diamond, each carbon atom is locked into a rigid 3D lattice with 4 others, making it the hardest substance we know. On the right, in graphite, each carbon bonds to 3 others in flat sheets that just slide right past each other. That's why it's so soft and slippery. It's the same exact element, just arranged differently.
And that right there is the secret we were looking for. The paradox is solved. Carbon isn't common, but its unique ability to form 4 strong, stable, and flexible covalent bonds, especially with itself, gives it a power to combine and create that's completely unmatched by any other element. It really is the ultimate molecular Lego brick.
Which leaves us with one final thought to chew on. We've just seen how simply rearranging carbon atoms can turn the soft lead in your pencil into the hardest diamond on Earth. So here's the question to ponder. What other materials that we use every day are just a different arrangement of the same basic parts? What other secrets are hiding out there, not in the ingredients themselves, but in the way they're put together?